Hello, welcome to anyone to this new tutorial on Copernicus services. My name is Álvaro Pascual Collar. I am consultant in allowing oceanic weather systems. In this tutorial, we will see how Copernicus services can provide data to analyze the impact of El Niño southern oscillation, also known as ENSO. And to do that, we will use Python and in the framework of Jupyter Notebooks run in a Jupyter Hub provided by the workshop. Here we will learn how to plot time series of an ENSO indicator, and also we will learn how to download data from Copernicus Data Store using the Copernicus Marine client, something really new. That is being implemented in Copernicus services. And also we will learn and we will see how to plot maps of anomalies to analyze the impact of El Niño over different oceanic variables. But first of all, let me explain you how to access these contents. Here you have the home page of the course. Up here you have a tag to the Jupyter Notebooks. This tag brings you to this area where all the contents related to Jupyter Notebooks are included. I have to say that before starting to work, the first thing you need is to be registered in Copernicus Marine Services. If you are not registered yet, you will need to access this link and follow the registration to get a password to the system. And also, I want to stress these other two options that are documentation, where you can find information about how you can download all the contents we are going to explain here today. And you can run these contents directly in your personal computer. So you can use it for your own purposes and freely modified. And well, as I said before, we are run this tutorial under the Jupyter Hub access. So to do that, you have to follow this link. And you will find that here you have to register with your username and password from Copernicus services. You can use your own username and your password and click on login. Jupyter Notebooks and LL, we see the Training Asia directory, which is the directory we need, right? So we can come back to our home directory by using cd:/. And we can copy this Training Asia 2024 by using the command copy -r because it's a recursive copy. And we have to write the source, which is Jupyter Notebooks and Training Asia 2024. And we have also to specify the destination of the copy, which is symbolized with a dot. This symbol means that we want to copy this directory, Training Asia, in the directory where we are currently are. We click enter. And well, once we have done this, you can see now, we have the Training Asia 2024 directory inside our home. So now we are in a situation of start to run the tutorial. We can close directly this window, and through using the file browser, we can navigate inside the directory and open directly this file, the notebook beginning and intermediate Asia 2024. As you know, this is tutorial devoted to make an analysis of El Niño Southern Oscillation. In this, through this tutorial, we will go over 5 different sections to plot in different El Niño index and El Niño index, and we will learn how to download data with Copernicus Marine Client, and we are going to plot maps of anomalies, and we will learn how to select data to plot El Niño and La Niña patterns maps of anomalies of El Niño associated to El Niño and La Niña patterns. Well, in this first section, we just provide a first introduction to El Niño oscillation. I don't want to spend much time on this because the tutorial is long. You probably know the El Niño Southern Oscillation is a large-scale warming event in the equatorial Pacific Ocean. There is a normal situation, a neutral situation of temperature and oceanographic situation, an atmospheric situation, which is in the equatorial Pacific, which is a situation where we have the trade winds along the equator that blows towards the west, and this the transport associated to this wind implies the upwelling processes here in the east coast of the equatorial Pacific, and accumulation of warm water here in the east side of the tropical Pacific near New Guinea and Philippines, right? This has some implications in atmospheric processes like the precipitations here in the west side of the tropical Pacific, and also it has other oceanographic implications. For example, the mixed layer depth, because this transport produce a reduction of the mixed layer depth here in the east coast, and it produces also a thicker mixed layer depth here, here in the west coast. Well, this situation is not static. This situation is more or less the mean situation between two extreme situations that we would usually call El Niño and La Niña. Under the Niño pattern, the trade winds are weaker than the average, so the accumulation of warm water near New Guinea is translated towards the west, towards the east. So the accumulation of water at the end is very close to the American coast, and in the other side, in the west coast of the equatorial Pacific, we have cooler anomalies of temperature. This also has implications in atmospheric processes, and also it has implications in the mixed layer depth. In this case, in the case of El Niño, the Niño pattern implies more homogeneous thick of the mixed layer depth. And in the case of La Niña, it's exactly the opposite. We have intensification of the trade winds. That means more accumulation of warm water in New Guinea and Philippines, and also it is associated with an increase of the upwelling processes here in the east coast of the tropical Pacific, right? Well, these processes has implications all over the world because has teleconnections with many features of atmospheric and oceanographic features. all over the world. So in this tutorial, we are going to see how the alternance between these two patterns, El Niño and La Niña, can have implications in the coast of Asia. Well, in this tutorial, we are working with Python, and so for people who is familiar with Python probably knows that the first lines in Python, we usually include these lines where we import the libraries we will use along the script. For example, here we're importing a library called NumPy, XRI, Pandas, Matplotlib, Cartopy, and Copernicus Marine Client. When we import a library, usually we use an alias for that library. So, for example, we import the NumPy library, and we use, from now on, we use the alias np. So from now on, every time we write np dot, we are referring to this NumPy library. Here I give you some documentation about the libraries we are using on this tutorial. I don't want to spend much time on this. I just will say that the NumPy, XRI, and Pandas libraries are libraries associated to the managing of numerical data. For example, NumPy, it's especially devoted and very useful to managing n-dimensional arrays, and XRI, it's very useful for accessing netctf files, files formatted in netctf format. We'll talk about this later. And Pandas, we will use Pandas to managing dates. And we will use also two plotting libraries, very famous, Matplotlib and Cartopy. Here, as I said before, you have the link to the documentation of any library, so you can explore deeper in deep what are the capabilities of these libraries and the functions of these libraries. And finally, we are going to use the new library that is being developed in the framework of Copernicus services, which is the Copernicus Marine Client. This library, it's very important because it allows to the user to access the Marine Data Store using Python commands and automating everything. So it's very, very useful. Here, as before, you have the link for the main pages of documentation of the library. But for sure, we will talk about this library later. As you probably know, in Jupyter Notebooks, we usually have this kind of structure where the documentation, we insert in the middle of documentation some cells that can be run in the system, directly run, and we navigate through the results. So to do that, we have to select this cell and click the run button. This run button is located up here. So you will see that when we click on the run button, there will appear here a little asterisk while the cell is running, and when the cell finishes, there appear a number which is the identification number of the run. For example, if we run this cell, well, with this, 29, this is strange. Let me restart the kernel, just. Well, we are going to run again this cell. You see the asterisk, and well, after this is better. This is the first cell we have run, and we obtain a number 1 here. which is the expected result. And with this, we have imported all the libraries we need for this tutorial, and we can continue, right? Here I give you some information of the datasets we are using in this tutorial. In this tutorial, we are going to work with two different datasets, Copernicus datasets. The first one is OMI, an ocean monitoring indicator developed by Copernicus Services. Here you have the links to the documentation of these products, to these products. Here you have this Niño 3.4 sea surface temperature anomalies is just an indicator that gives information of the El Niño state. This is the web page of the Copernicus data store. You can see here that this is just an OMI, a time series of the sea surface temperature anomaly in the region, the standard region Niño 3.4, which is a region located in the center Pacific, Equatorial Pacific. And this indicator is highly associated to the patterns of El Niño and La Niña. So if we see here, the indicator gives just a time series that when these time series are positive, are greater than 0, are associated with periods where the El Niño pattern is dominant, and when this indicator has values under 0, is an indication that the La Niña pattern is stronger, and we have this. We can expect the conditions of La Niña, right? As any Copernicus product, this page is associated with the user manual and the quality information document. These two documents are really, really important inside any Copernicus product. I highly recommend that any user that is accessing to a new product in Copernicus before start to work, have a look to these two documents. Is really, really important, because these two documents gives all the information all the technical information that gives you the knowledge about what is the product, how has been developed, and how is stored. Information is very technical, these documents. And also the quality information document is the document that gives you information about this product, about the performance of this product, and when this product can be reliable, and if it has some difficulties in some situations or some regions. So it's really interesting to have a look to these documents before using any Copernicus product. This is a first product we are going to use in our tutorial, and also we are going to use this global multi-year fee product. This is a product of reanalysis, a global reanalysis of the sea, physical reanalysis that give us information of physical parameters like temperature, sea surface temperature, seawater salinity, current, ocean mixed layer thickness, etc. Sea surface height, etc. Right? Well, with this, we can jump into the first section where we are working. Well, and after that, we are going to use 2 times the bar function. Let me run this and we will see the result of this. The bar function is devoted to create histograms. As you can see here, we have the previous function we defined before, the blue line with the grades added area, as we did before. But in this plot, we are also including the information of annual means in format of an histogram with orange bars in positive values and olive bars in negative values, right? So this is what we are doing with these two functions. From Matplotlib, we use the bar function with time, annual mean, and in color orange. With this, we are plotting all bars, but since we want to plot in green, in olive color, in green, the negative bars, we have to use npwhere, another function of NumPy. It's very famous. npwhere is a function devoted to select a specific data of a variable that meets a condition. For example, with this, we are selecting the data of annual mean that meets the condition of being less than 0, right? So with this, we are selecting this data, and to plot only this data, you can compare this line and this line, and you realize that to plot only this data, the data that meets that the value is less than 0, we are plotting the time values, selecting according to cell I, and the annual mean, selecting the values we want to select, right? So with this, we obtain this plot. With this, we have a different view of the El Niño index. You can see here we can take some conclusions. For example, we can say that the year 1999 was a year strongly influenced by La Niña pattern, as well as the year 2000. And regarding the Niño pattern, we can see that the year 1987 and also 2015 were strongly influenced by El Niño pattern, right? So let's take a look to what happened in these years. Let's make in this next section we will have a look to the maps of anomalies associated to these years. We will keep in mind this information we have. The year 1999 was associated to La Niña pattern and strongly influenced by La Niña pattern, and the year 2015 was strongly influenced by El Niño pattern. Well, with this we can jump to the next section. Here, we are going to learn to download some Copernicus Marine client, some Copernicus products, because, well, as we said before, we want to see what happened in these years. So to do that, we are going to download information of a graded product. For example, we are going to download information or data from global multi-year analysis product. This product, here you have the link to the product, the Copernicus product, and with this, as I said before, here you have the access to the user manual and the quality information document. Really recommended to have a look to these documents before using any product of the catalog. And we have this button where we can download the data of the product. We can download the data of Copernicus data using this web page, which, okay, is a good way to do it. You can follow this web page where you can select the dataset you want. As you see, the product has many different datasets. The differences between these datasets, as I said before, these are shown in the user manual. So if you want to use data of this product, the first thing you need is to go over the user manual to see what dataset is the dataset you really need, right? and the differences, etc. You can also select the variables, etc. For example, you can want to see surface high above geoid and see what the potential temperature. These are the variables we are going to use in our example, these three variables, and you can select the window you want to download and the dates, etc. Well, this is a good way to download data, but in this case, I want to center in the use of Copernicus Marine Client. This Copernicus Marine Client is very interesting library developed by Copernicus, and it's a library that allows to the user to automate the downloading of data and downloading data using Python commands directly. So let's see how to download this dataset using Copernicus Marine Client. First of all, we will go over a very interesting function of Copernicus Marine Client, which is the login function. It's a very simple function that works like this. You only have to run the function, and with this you can log into the system, so you don't need to use again any password or any username. So you have to log into the system using your credentials for Copernicus services. I will write mine. And as you can see here, password. And then, well, it asks if you want to override the credentials, yes. And when you have here a true, you receive a true, you are logged in the system and you don't have to log again until you log out. So you won't need to pass over this step again. And well, after that, we can go over the next cell. That is the cell where we are downloading the data we need for the next step. Here you can see that we have a new function of Copernicus Marine Client, which is a function called subset. It's a very interesting function because in this function you have a lot of parameters, but with these parameters you specify the data set you want to download, and you specify all the information you need to download data. It's maybe the same than in the Copernicus web page, but only you have to write it in code. For example, you have to define the dataset ID, the variables you want, the minimum longitude, maximum longitude, start date and time, the minimum depth, etc. And also you have to specify the output file and the output directory. As you can see here, we are extracted these variables, the data path, data file, and we are using the variables outside of the function. We are defining the variables outside of the function, so this is more simple when you want to play with this function, downloading different data. It's easier to change here the maximum and minimum latitude. And we also have a list of variables that correspond to sea surface temperature, sea surface height, and mixed layer depth. How do we know these parameters? Well, it's very simple. You can go to the Copernicus Web Services and click on this button. In this button, once you have selected the variables you want or the times you want to download, you will get the information you need for the command subset. You see here you have the configuration of the command, the dataset ID, and also the list of variables. So it's really simple. Once you have this configuration one time, it's really simple to later to includes modifications, for example, to download different windows of data or different periods of time or different depths, etc. Or even different variables, right? Because you only have to change this list of variables. Well, we will run this cell to download the data because, as you can see, we are going to store our data in the data directory. This directory that currently is empty, and also we will call this data file with this name, Kemems Glorea NC, because it's going to be an HCDF file. Well, let's run this cell. And here you have to accept the downloading. As you can see, we are downloading about 2 GB of data, and it's really, really fast. The accessing of data and the download data of data is really, really fast. And with this, we have in our system the data file we have downloaded. Here, there is, doesn't appear here, but I can assure that the data is in the system. For example, we can go to MarineData4Asia and data. Here you can see that we have the Kemems Glorea file, right? Don't know why the file browser is not working right now. Maybe because this. Okay, it was just trying to look for a specific pattern. You can see here in data we have the two files. The first file we have in the beginning of the tutorial, and we have also downloaded our file here, right? Well, once we have the file to work, we can continue our work. As you remember, we wanted to make an analysis of 1999 and also 2015 to see the anomalies of temperature and how the El Niño and La Niña pattern affect the anomalies of temperature, not only near New Guinea and Philippines, but also near the coast of in the Gulf of Bengal and the South China Seas. So we jump into the next section, plotting maps of anomalies. And here we have a new cell where this has information that we already seen in this tutorial. We define the name of the data file, which is stored in data, and the name of the file, netcdf. And we open the file, including this information in a new variable that is called ds. And here we include some differences than respecting before. For example, once we have downloaded the information we will need, since we want to work with anomalies, we will compute the climatic mean of the values of the dataset. So we will compute the mean. We will use the function mean over the dimension time, right? So we will store this information in mean ds. And also we will be interested on the annual means because we want to analyze years, right? So as we did before, we have to combine the functions group by and mean, so we can compute the annual mean of the dataset we have opened. Here we will print, let me run this, we will print the result of this cell. This can take a few seconds because, well, computing the mean of all data, but it's here, yes, it's done. as you can see in the annual mean data set, we obtain the information of the data set, but we have, the first thing we have done is to compute the annual means of the data set. So we have a data set with 4 different dimensions. Depth, this depth only has one step. And we have latitude, longitude, and year. We have more than 500 steps of latitude, more than 900 steps of longitude, and 29 steps of time. Since this is annual means, we have 29 years of data, right? We have changed with this the data that comes in. Well, we can make this exercise. For example, we can create a new cell where we print the DS object. As you can see here, the DS object, which is the DS we are open from the file, is an object that has about more than 300 time steps. And if we go over the time, we see that the values are in monthly means. It starts in February, March, April, May, etc. But in our case, in annual mean, yes, we have only 29 values, and these values are not dates, are actually years. 1993, 94, 95, etc. up to 2021, right? Well, we have the annual means of the data set, and next we are going to select the data we want to plot. To do that, we are going to run this cell. In this cell, we are selecting the specific data we want to plot. As you remember, we wanted to analyze the year 1999 and 2015. And we want to analyze the variable sea surface temperature that, as I said before, as you can see here, the variables stored in the annual mean dataset is ZAO, THOS, and MLOST. How do we know that what is the information stored in these 3 strange names? Well, we can open these the attributes of each variable, and here we will see that seawater potential temperature, this variable, stores information of seawater potential temperature. This variable stores the sea surface height above geoid, sea surface height, and this variable stores the mixed layer depth, right? So we are going to work in this example with ZAO, the sea surface temperature. So we select the variable name ZAO, and the years here we are defining a list of years of interest. In this case, we will plot just 2 years, which are 1999 and 2015. As we said before, 1999 is associated to La Niña pattern, and 2015 is associated to El Niño pattern, right? In this loop, we are looping over the years selected in this list, and we use a very common function from XRI, that is the cell function. Is a function that allows us to select specific values of a variable. So, for example, for every year in year list, we are selecting the data associated to this year. The method is nearest, and after that, since we don't want to work with data, we prefer to work with anomalies. We compute the anomalies and we store the anomalies in a dictionary. This is a common way to work in Python using dictionaries, so all the information is ordered. So the selected data for the specific year, we compute the anomaly subtracting the annual mean, the climatic mean, over the selected data, on the selected data. Well, and we store this information in the dictionary anom data dict, right? Let's run this cell. And well, here we have a dictionary that has two elements, the values for the year 1999 and also the values for the year 2015. And once we have selected the data and computed the anomalies, we can create a new function to plot our results. So here you have, we have created in this cell a new plot anom map function. That is a function that we have called plot anom map. In this function, we have included 4 different sections that are devoted to create the figure as before. Here there are information of editing the basic map features, for example, at the borders of countries, the land mass, and the coastlines, or etc. And also we have a section where we are plotting the data, the specific data, and we are using the function pcolor, which is a function from matplotlib that is devoted to create pseudocolor plots. And also at the end of the function, we are including the final editing commands like include the title. Let me run this function. Like include the title in the figure and also include the color bar. Here you can see that since we are using a function that we want to plot anomalies, anomalies are usually plotted with specific color bars, a color bar that goes from blue to white to red. So the negative colors appear colored in blue colors, and the positive values are associated to red. So this is what we are doing here in CMap lim. We are computing the limits of the data, the minimum of the data and the maximum of the data, and we use this information here in the plotting of the map. So we are defining the limits of the color scale, right? Here we have the results for the year 1999 and 2015. As you can see here, we have something that is what it could be expected according to theory. The year 1999 is associated to La Niña pattern, so we can see positive anomalies around New Guinea. And well, what we didn't know until now is the anomalies associated in the Gulf of Bengal and also in the South China Seas. And also we can see how the year 2015 was characterized by negative anomalies of temperature, surface temperature around New Guinea and Filipinas, and very positive, high positive anomalies in the Gulf of Bengal and also in the South China Sea. As you can see here, this is a very interesting result. We are analyzing the pattern of the year, but as you can see, maybe for this is not something not expected. Here we don't have very high warm temperatures. Maybe it's not as warm as we could imagine according to the theory, and this is actually because we are analyzing specific years. These years are not are not only affected by El Niño and La Niña oscillation, they are affected by many other features and many other processes, atmospheric and oceanographic. So despite of the Niña index it has a specific value, the result of a specific year may have divergences with what it is expected with the with taking the theory, right? So, well, how can we adapt this? How can we get the information of, or how can we compute the real pattern associated to El Niño and La Niña? Well, this is what we are going to see in the next section, the plotting El Niño and La Niña patterns. Here we have only this section is quite short actually, because we are using all the functions we used to plot before. For example, as you can see here, we are using plot anomap, which is the function, the plotting function we define here. So with this, we have not to replicate the code. We can use the same code to run repeatedly. And well, to plot El Niño and La Niña patterns, first of all, we have to think how can we plot the specific patterns. Well, for that we can use our analysis of El Niño index, because imagine we can plot only the average of the years that are associated to positive values of El Niño index, or if we could make an average of the years of the that has characterized by negative values of El Niño index. With that, we would obtain what we usually call composites, which are averages of years, specific years grouped by one specific feature. And this is what we are going to do now. We are going to select the years that has positive values of anomalies of El Niño index, and years with negative anomalies, and we are compute the sea surface temperature, the average of sea surface temperature only over these years and only over these years. And we will plot the anomalies of these patterns to see if these years are associated to a specific pattern, right? Here, that is what we do here in this cell. In this first cell, we are selecting the years of positive and negative Niño 3.4 index and computing the averages. Actually, this is a little mistake. We are not compute the averages. Sorry. With this, we are selecting the values of positive and negative Niño 3.5 index. You can see here, I will run this cell. You can see here we are using again the function where. This function is, as I explained before, is a function of XRI that is devoted to select the values of a specific variable that meets a specific condition, right? So here we are selecting the values of annual mean Niño that are greater than 0, and we are selecting the values of annual mean Niño. This is the values of the El Niño index that are less than 0, right? And with this, we are selecting the years, the specific years of El Niño that are associated to these values, right? These values associated to the positive or negative El Niño mean, right? So with this, we are creating two new variables, year positive and year negative. And you can see here that is very simple. We get the first variable, year positive, has the list of years we need, 1993, 94, 97, 2002. And we also have a list for years negative, 95, 1985, 96, 98, 2013, etc. With this, we can compute now. Yes, we are computing the averages of the data with these lines. Again, since we are computing averages, we are selecting the data associated to the GR positive and the GR negative. And after selecting the data using the cell function that we explained before, after selecting the data for the GRs, the list of GRs positive and negative, we are computing the mean for the GR, right? So we can run this cell here. And once we have the mean of the data positive and the mean of the data negative, we can display these two variables. We run the cell again, and we obtain, as you can see here, the values of the averages of this of annual mean of the dataset selecting only the specific GRs associated to the positive Niño index or negative Niño index, right? And with this, we are almost at the end of the tutorial, because we only need to compute the anomalies of this data. As you can remember, the mean positive is the variable associated to the positive values of El Niño and negative values of El Niño, and we are computing the anomalies by subtracting from this array the array of climatic mean, right? And we use these values to plot, and we use these values to plot an anomaly map, as we did before. This can take a few seconds. As you can see here, we are doing the same 2 times. First, we are plotting the map of positive anomalies, the anomalies associated to the positive El Niño index. And after that, we are doing exactly the same, but plotting the values associated to negative values of El Niño index. Here we have the result. You can see here we have the real patterns of El Niño and La Niña. For example, for positive El Niño 3.4 index, we have clear negative anomalies in a situation of El Niño. We have clear anomalies of sea surface temperature around New Guinea, and we have clear positive anomalies in the Gulf of Bengal. And also we have the inverse in the case of La Niña. We have positive anomalies around New Guinea and Filipinas, and in the Gulf of Bengal we have negative anomalies. In this case, you can see that, we can see the South China Sea that has a different pattern than we see before. We see before very clear patterns, but here we can see that the South China Sea is affected in different ways. The areas close to the coast, let's see, are positively affected by El Niño index. So under the Niño conditions, they tend to have positive anomalies of temperature near to the coast and negative anomalies of temperature offshore, let's say. And we have the inverse pattern in case of La Niña. Well, this is the finish of this tutorial. I hope you enjoyed the tutorial. Here I give you some exercises. With this code you can change the name of the variable we are using, but I give you this exercise for you to play with the code and make the change you want, and you will get custom with this code. So if you can run again this code changing here the name of the variable you are analyzing is in this cell here. You can change the name of the variable in this cell, so you can make this analysis not only for sea surface temperature, but also for sea surface height, for the elevation of the surface of the sea, and also for the mixed layer depth, and take your own conclusions. Well, thank you very much for attending to this tutorial. I hope you really enjoy this tutorial, and I will see you in the next one.